Picture this: a single ship gliding silently through the fabric of space, its hull bathed in the eerie glow of a tunnel carved through reality itself. The stars stretch and warp around it, bending like liquid light as the vessel slips through a gateway older than time. This isn't science fiction. This could be the future, or perhaps the distant past. Because what if humanity wasn't the first to unlock the secrets of wormhole travel? What if, buried in the cosmos, there are echoes of journeys taken billions of years ago by civilizations lost to the ages? Today, we're diving into one of the most thrilling mysteries of our universe, the enigma of its first wormhole travelers. From the wild theories that suggest black holes might be ancient transit hubs, to the mind-bending idea that wormholes could be hiding in plain sight, woven into the very structure of spacetime, we're about to explore 30 groundbreaking possibilities that could rewrite everything we know about reality. Wormholes have long been the stuff of dreams, cosmic shortcuts linking distant corners of the universe, or even bridges between parallel realities. But what if they're more than just theoretical curiosities? What if they've already been used? Imagine a civilization so advanced, so far ahead of us, that they mastered spacetime itself, leaving behind faint traces of their voyages like cosmic breadcrumbs. Some scientists speculate that if wormholes were ever created, their signatures might still linger hidden in the faint ripples of gravity, or encoded in the mysterious radiation humming between galaxies. Others go even further, suggesting that the universe's very first wormhole might have been a naturally occurring phenomenon, a fleeting crack in reality forged in the chaos of the Big Bang. This is where the adventure begins. Over the next 30 theories, we'll unravel the tantalizing clues that could point to humanity's next great leap, or reveal that we're not the first to take it. From the bleeding edge of astrophysics to the wild frontiers of theoretical speculation, we'll examine the evidence, the myths, and the startling possibilities that could change our understanding of existence. So buckle up. Whether you're a seasoned space enthusiast or just curious about the universe's greatest secrets, this journey will challenge everything you thought you knew, and maybe, just maybe, leave you wondering, if wormholes are real, who or what might have traveled them first? Long before wormholes became a staple of science fiction, they emerged from the pages of hard science, specifically from the equations of Albert Einstein and his colleague Nathan Rosen. What we now call an Einstein-Rosen Bridge began as a mathematical curiosity, a strange but inevitable consequence of general relativity. Picture spacetime as a vast, flexible sheet. When massive objects like stars warp this fabric, they don't just create dips, they can, in theory, twist it into tunnels. These tunnels wouldn't just connect two points in space, they'd stitch them together like hidden doorways in the cosmos. The beauty of Einstein and Rosen's work is that it didn't require any speculative physics. Their bridges arose purely from the math of black holes. When a star collapses, it doesn't just vanish into a singularity. It might forge a throat, a tunnel leading somewhere else. The catch: these early wormholes would be brutally unstable. Without some exotic material to prop them open, they'd snap shut faster than light could traverse them, crushing anything inside. But here's the tantalizing part. What if nature found a way? Some theorists speculate that in the extreme conditions just after the Big Bang, quantum fluctuations or dark energy might have briefly stabilized these bridges, creating the universe's first natural wormholes. Think of it like an ancient, crumbling bridge across a canyon. Even if most of it has collapsed, traces of its foundations might remain. If primordial wormholes ever existed, their remnants could still linger hidden in the gravitational echoes of the early universe, or disguised as rogue black holes with peculiar properties. And if that's true, then the first travelers through these tunnels wouldn't have been civilizations with advanced technology, but particles or energy itself, hurled through cosmic shortcuts by the violent physics of creation. That's the wild promise of Einstein-Rosen bridges. They suggest wormholes aren't just possible, they might have been inevitable, woven into the universe from the very beginning. At the smallest scales of the universe, where the fabric of spacetime churns like a turbulent sea, something extraordinary may be happening. Welcome to the realm of quantum foam, a frothing, chaotic landscape where tiny wormholes could blink in and out of existence faster than the flicker of a thought. This isn't just wild speculation, it's a serious idea rooted in the bizarre rules of quantum mechanics. Picture spacetime not as a smooth, unbroken sheet, but as a bubbling soup of microscopic tunnels, constantly forming and collapsing in a dance of raw cosmic energy. For decades, physicists like John Wheeler theorized that at distances a trillion times smaller than an atom, spacetime might lose its smoothness entirely. Instead, it could become a seething foam of virtual particles, black holes, and yes, wormholes. These wouldn't be the grand cosmic highways of science fiction, but fleeting, microscopic shortcuts. The catch, they'd vanish almost instantly, far too quickly for anything to pass through. But here's where the theory gets mind-bending. What if an advanced civilization found a way to catch one of these quantum wormholes and stretch it, stabilize it, transform it into something usable? Imagine a civilization with technology beyond our wildest dreams, one that could harvest these tiny spacetime defects, inject them with exotic matter or negative energy to keep them from collapsing, and slowly expand them into stable passageways. It sounds like magic, but the math suggests it might be possible. Some researchers speculate that the key lies in manipulating the vacuum energy of spacetime itself, essentially taming the quantum foam's chaos. And if that's true, then the universe's first wormhole travelers might not have needed to create wormholes from scratch. They could have simply plucked them from the quantum underworld, like forging roads out of the cosmic static. This idea reshapes how we think about interstellar travel. Instead of building massive structures or warping spacetime with unthinkable energy, an advanced species might have mastered the art of quantum gardening, cultivating the universe's tiniest wrinkles into something far greater. The implications are staggering. If wormholes can be grown this way, they could be scattered everywhere, hidden in plain sight, woven into the very fabric of reality. Maybe we've already detected their faint signatures in particle collisions or gravitational anomalies without even realizing it. The quantum foam hypothesis doesn't just offer a roadmap for future travel, it suggests the cosmos might be riddled with dormant wormholes, remnants of ancient civilizations or natural processes we don't yet understand. And if that's the case, then the universe's first travelers might not have been explorers in ships, but something far stranger: particles, energy, or entities we can't yet imagine, slipping through spacetime's cracks in the darkness of the quantum deep. But even if wormholes exist in nature or can be coaxed from the quantum foam, they share one critical flaw: they're horrifically unstable. The moment one forms, gravity wants to slam it shut like a cosmic bear trap, crushing anything inside. So how could anything or anyone ever traverse such a tunnel? The answer lies in one of the most elusive substances in theoretical physics: exotic matter with negative energy. Unlike ordinary matter, which gravitates inward, negative energy would exert a kind of anti-gravity, pushing outward against the wormhole's collapsing walls. Think of it like threading a needle with a balloon. If the balloon's pressure keeps the needle's eye open, you can pass a string through. Negative energy would do the same for a wormhole, propping it open just long enough for something to slip through. The problem: we've never found proof such matter exists. The closest we've come is the Casimir effect, where quantum fluctuations in a vacuum create a tiny region of negative pressure between two metal plates. It's a faint whisper of the phenomenon, but it hints that the universe might allow this strange energy under the right conditions. Harnessing enough negative energy to stabilize a macroscopic wormhole would require technology beyond anything we can imagine today. Some calculations suggest you'd need the equivalent of a star's worth of this exotic material just to keep a tunnel open long enough for a single ship to pass. But here's where things get hopeful. Breakthroughs in quantum field theory suggest there might be workarounds. Certain configurations of electromagnetic fields or quantum vacuum states could generate localized negative energy without needing vast stockpiles of exotic matter. It's like discovering you don't need to build an entire dam to redirect a river, just the right arrangement of stones. The real puzzle is whether nature itself might have stumbled upon a solution. If wormholes existed in the early universe, could quantum fields or dark energy have temporarily provided the necessary negative energy? Some models suggest that during cosmic inflation, the rapid expansion of spacetime might have stretched microscopic wormholes into larger, semi-stable structures. If true, the first travelers through these tunnels wouldn't have needed technology at all. They might have ridden the universe's own explosive birth pangs. This raises a provocative thought. If negative energy is the key to wormhole travel, then detecting its signatures, whether in lab experiments or deep space observations, could be our first real clue that these cosmic shortcuts are more than just equations on a chalkboard. And if we ever learn to produce or manipulate it, humanity might not just be searching for ancient wormholes, we could be building our own. Black holes are cosmic powerhouses capable of warping spacetime to extremes we can barely fathom. But what happens when two of these gravitational titans collide? The energy released is so immense that it sends ripples through the very fabric of the universe, ripples we've detected as gravitational waves. Yet buried in that chaos might be something even more extraordinary, the birth of a wormhole. When black holes merge, their singularities don't just combine. They could twist spacetime into a temporary bridge, a fleeting tunnel between distant points in the cosmos. The math behind this is as beautiful as it is wild. General relativity predicts that under the right conditions, the violent dance of merging black holes might not just form a new, larger black hole. It could stitch together a throat of spacetime, a shortcut that exists for only a fraction of a second before collapsing. Think of it like two whirlpools in a cosmic ocean spinning into each other. For a brief moment, their vortices might connect, creating a passage before the water crashes back into equilibrium. That's the essence of a black hole collision wormhole, an ephemeral bridge forged in the universe's most violent events. But here's the catch. For such a wormhole to last long enough to be traversable, even hypothetically, the black holes would need very specific properties. They'd likely need to be spinning at nearly the speed of light, their rotations aligned in just the right way to twist spacetime into a stable enough shape. Some theories even suggest that if these black holes were threaded with cosmic strings, hypothetical, ultra-dense remnants from the early universe, the resulting wormhole might stay open slightly longer. It's a perfect storm of conditions, one that might have been more common in the chaotic early universe than it is today. So could these collisions have created the first natural wormholes? If the universe was once packed with primordial black holes, constantly merging in the dense soup of the early cosmos, then fleeting wormholes might have been as common as stars in today's night sky. And if that's true, then the first travelers through them wouldn't have been ships or civilizations, but raw energy, particles, or even strange forms of matter we don't yet understand, hurled through these tunnels by pure cosmic chance. The echoes of these events might still be detectable. Gravitational wave observatories like LIGO and Virgo have already caught the reverberations of black hole mergers. If a collision ever produced a wormhole, even a short-lived one, it could leave a subtle fingerprint in the gravitational wave signal, a slight delay or echo as spacetime itself briefly folds into a tunnel. No such anomaly has been found yet, but as our detectors grow more sensitive, we might just catch a glimpse of spacetime's hidden architecture. This idea blurs the line between destruction and creation. Black hole collisions, long seen as the universe's most cataclysmic endings, could also be the genesis points of something far stranger. brief doorways threading the cosmos together. And if nature found a way to weave these tunnels once, who's to say it couldn't happen again, or that some civilization somewhere hasn't already learned to harness them? Cosmic strings sound like something ripped straight from science fiction, thin, unimaginably dense filaments stretching across the universe, thinner than an atom but with the mass of entire galaxies. These bizarre structures aren't just theoretical oddities. They could be the universe's ultimate construction workers, warping space-time so severely that they twist it into wormholes. Picture a tightrope stretched between two distant points in space. Now imagine that rope is so heavy it bends the very fabric of reality beneath it, dipping close enough to another cosmic string that their gravitational pull stitches a tunnel between them. That's the essence of how these hypothetical defects could forge natural wormholes, not through technology, but through raw cosmic geometry. The idea stems from the early universe, a time of extreme energy and phase transitions. As the cosmos cooled, cracks might have formed in space-time, like fissures in ice as water freezes. These cracks would be cosmic strings, relics of a more symmetric universe, now floating like ghostly threads through the void. Their gravitational influence is staggering. A single string just a kilometer long could weigh more than Earth, curving space-time around it like a bowling ball on a trampoline. If two such strings were to pass near each other, or if one looped back on itself, the resulting distortion could pinch space-time into a tunnel, a wormhole held open not by exotic matter but by pure gravitational torque. Here's where it gets even wilder. These cosmic string wormholes wouldn't need to be artificially stabilized. Their immense mass and topology could keep them naturally open, at least long enough for travel. Some models suggest that in the early universe, networks of cosmic strings might have woven a labyrinth of shortcuts, a primordial subway system threading through the cosmos. If advanced civilizations existed back then, or if natural processes hurled matter through these tunnels, the first interstellar journeys might have happened billions of years before Earth even formed. But how would we find evidence of such strings today? The hunt is already on. Cosmic strings would leave distinct imprints, sharp jumps in the cosmic microwave background, bizarre gravitational lensing effects, or even ripples in spacetime itself. Some astronomers speculate that certain unexplained gravitational wave signals or oddly warped galaxies could hint at strings lurking in the cosmic shadows. And if we ever spot one, it wouldn't just confirm a bold theory, it could point us toward the universe's oldest, most durable wormholes, frozen in time like spider silk across the ages. The poetic beauty of this idea is that it turns the cosmos into a sort of self-assembling maze, where the universe's own wrinkles might have created highways for travel. Whether any civilization ever used them remains a mystery, but the possibility lingers like whispers in an endless corridor echoing from the dawn of time. Black holes famously devour everything, even light can't escape their grasp. But what if each black hole has a cosmic counterpart, a place where all that swallowed matter isn't destroyed but expelled? Enter white holes, the theoretical opposites of black holes. Where a black hole's gravity pulls inexorably inward, a white hole would violently repel everything, spewing out matter and energy like a cosmic fountain. And if these two phenomena are linked not just as opposites, but as connected ends of a wormhole, it would revolutionize our understanding of interstellar travel. The idea isn't as far-fetched as it sounds. Einstein's equations allow for white holes just as they predict black holes. Some models suggest that when matter falls into a black hole, it doesn't vanish into a singularity forever. Instead, it might emerge somewhere else, ejected from a white hole in another part of the universe, or even another time entirely. Picture it like a tunnel with two ends, one sucking matter in, the other blasting it out. That tunnel, it's a wormhole, a bridge stitching together distant corners of spacetime. But here's the catch: white holes are notoriously unstable. The moment they form, the sheer pressure of ejected matter would likely cause them to collapse. Unless, of course, something or someone figured out how to stabilize them. Imagine an advanced civilization harnessing the energy of a black hole to prop open its white hole counterpart, creating a permanent transit system. The implications are staggering. A network of black hole-white hole pairs could serve as a ready-made galactic highway, with entry and exit points scattered across the cosmos. The most tantalizing possibility, these connections might already exist in nature. Some theorists speculate that certain high-energy cosmic events, like the mysterious gamma-ray bursts that flare briefly in distant galaxies, could be signs of white holes activating. If true, the universe's first wormhole travelers might not have needed to build anything at all. They could have simply stumbled upon these natural portals, riding the ejections of white holes like cosmic surfers catching a wave. Detecting such a connection would require spotting the unique signatures of paired black and white holes, perhaps a black hole's gravitational pull, matched with an unexplained burst of energy light years away. No such pair has been found yet, but the search is on. And if we ever confirm their existence, it wouldn't just mean wormholes are real. It would suggest the universe has been quietly threading itself together all along, leaving behind a hidden roadmap for anyone bold enough to follow it. The Big Bang wasn't just the birth of matter and energy. It was the moment space-time itself burst into existence, stretched and twisted under forces we can barely comprehend. In that searing, chaotic infancy of the universe, the fabric of reality might have fractured in ways that left permanent scars, wormholes. Imagine the cosmos as a newborn, its space-time still pliable like molten glass cooling into shape. As it expanded and contorted, cracks and folds could have formed, not just on its surface but through it, tunnels threading the fiery early universe together. These wouldn't be the carefully constructed wormholes of far future engineers, but raw, primordial shortcuts forged in the furnace of creation. The math behind this is as elegant as it is profound. During the universe's rapid inflation phase, quantum fluctuations, tiny ripples in space-time, might have been stretched to cosmic scales. Some of these fluctuations could have pinched off into self-contained loops, creating structures known as traversable Lorentzian wormholes. Unlike the unstable Einstein-Rosen bridges, these tunnels might have been held open by the very conditions of the early universe: the intense energy density, the repulsive force of inflation, or even exotic fields that no longer exist today. It's like thinking of the Big Bang not just as an explosion, but as a cosmic loom, weaving space-time with threads that occasionally knotted into passageways. But here's the haunting question: if wormholes existed in that primordial era, what or who could have used them? The universe was too young for stars, let alone civilizations. Yet nature itself might have been the first traveler. High-energy particles, bursts of radiation, or even clumps of dark matter could have been hurled through these tunnels, redistributing energy and matter in ways that shape the cosmos we see today. Some researchers speculate that certain large-scale structures in the universe, unexpected voids or clusters of galaxies, might be the faint fingerprints of matter that took a shortcut billions of years ago. The most tantalizing clue could lie in the cosmic microwave background, the afterglow of the Big Bang. If wormholes warped space-time in the universe's first moments, they might have left imprints in this ancient light, subtle distortions or temperature fluctuations that defy conventional explanations. Scientists are already scouring this radiation for anomalies that could hint at space-time's hidden architecture. And if they find even a whisper of evidence, it wouldn't just confirm wormholes, it would rewrite our origin story, revealing that the universe's first shortcuts were etched into reality before time itself had settled into its rhythm. This idea transforms how we see the cosmos. Instead of waiting for advanced civilizations to build wormholes, nature might have provided them freely, woven into the universe's blueprint. The implications are staggering. If these tunnels survived the Big Bang's fury, they could still lurk in the darkness today, dormant relics of creation waiting to be rediscovered. And if that's true, then the greatest highways in the universe might not be our inventions, but inheritances from the dawn of everything. Dark matter is the universe's most persistent enigma, an invisible substance that outweighs ordinary matter 5 to 1, yet refuses to reveal itself except through its gravitational grip on galaxies. But what if this cosmic ghost isn't just lurking in the shadows? What if it's actively shaping the fabric of space-time, twisting it into tunnels we can't yet see? The idea that dark matter could be the hidden architect of wormholes isn't as far-fetched as it sounds. Picture dark matter not as scattered particles, but as vast, dense concentrations. Knots of gravitational influence so strong they warp space-time into bridges between distant points. These wouldn't be the delicate, unstable wormholes of theoretical models. They'd be robust, naturally occurring shortcuts, reinforced by the sheer gravitational heft of dark matter itself. Think of space-time as a trampoline with galaxies and clusters as weights pressing down. Dark matter's distribution creates deeper dips, places where the fabric is stretched thin. If enough of it clumps in just the right configuration, those dips could pinch together, forming a throat between two distant regions. Unlike the fleeting wormholes formed by black holes or quantum foam, dark matter's gravitational scaffolding might keep these tunnels open far longer, like a cosmic suspension bridge anchored in the invisible mass we can't see. Some theorists even speculate that dark matter's peculiar properties, its lack of interaction with light and ordinary matter, could act as a stabilizer, preventing the wormhole's collapse by counteracting the destructive forces that normally slam them shut. The most tantalizing evidence for this idea lies in the mysterious gravitational anomalies astronomers have observed. Certain regions of space bend light in ways that defy explanations based on visible matter alone. Could these distortions hint at something more profound, not just unseen mass, but hidden space-time tunnels woven into the cosmos? If so, the first travelers through these dark matter wormholes might have been particles or energies we don't yet understand, funneled through them by the universe's own invisible hand. Detecting such portals would require rethinking how we map dark matter's influence. Instead of searching for diffuse halos around galaxies, we might need to look for telltale gravitational signatures, strange lensing patterns, or sudden jumps in space-time curvature that suggest a tunnel's presence. Future telescopes and gravitational wave detectors could hold the key, revealing whether the universe's darkest corners hide the oldest roads ever built. And if they do, it would mean the greatest infrastructure in the cosmos wasn't engineered by civilizations, but by the universe itself, a network of highways carved from the very stuff we've spent decades trying to find. Imagine the universe as a vast, intricate hologram where every event, every particle, every ripple in space-time isn't truly three-dimensional, but a projection of information encoded on a distant, two-dimensional surface. This isn't science fiction, it's the holographic principle, a radical idea born from black hole physics that could rewrite our understanding of reality itself. And buried within its equations lies a startling possibility. Wormholes might not just bridge space, they could be cosmic data streams, tunneling information between dimensions in ways that make them the universe's oldest communication network. At its core, the holographic principle suggests that all the information in a volume of space, every star, every atom, even the fabric of space-time, can be represented as bits of data painted on its boundary, like a holographic image emerging from a flat surface. If this is true, then the three-dimensional universe we experience might just be a shadow of a deeper, more fundamental reality. But here's where wormholes enter the picture. Some theorists propose that these tunnels could act as quantum fiber optic cables, ferrying information between the holographic surface and the projected spacetime we inhabit. Think of it like a cosmic fax machine. A wormhole wouldn't just move matter from point A to point B, it could transmit the very code that defines those points, rewriting reality as it goes. This idea gains traction when you consider black holes, the holographic principle's birthplace. According to the theory, all the information swallowed by a black hole isn't lost. It's smeared across its event horizon, the ultimate holographic screen. Wormholes could be the secret tunnels that preserve this information, linking the horizon's data to the singularity inside. In this view, the first travelers through wormholes might not have been ships or particles, but information itself, quantum bits leaping between dimensions, stitching the universe together from the inside out. The implications are dizzying. If wormholes are holographic data conduits, then traversing one wouldn't just transport you across space. It might rewrite your very structure, translating you from one cosmic language to another. An advanced civilization harnessing this could use wormholes not just for travel, but for computation or even reality manipulation, tweaking the universe's source code by sending carefully crafted signals through these tunnels. Even more provocative is the idea that the universe's first wormholes might have been accidental byproducts of this holographic encoding. In the fiery moments after the Big Bang, as space-time crystallized from whatever lies beneath, cracks could have formed, wormholes serving as emergency release valves for overflowing information. If so, remnants of these primordial data highways might still lurk in the cosmos, their presence betrayed by subtle glitches in quantum entanglement or anomalies in cosmic radiation. Detecting such relics would require rethinking how we observe the universe. Instead of searching for gravitational distortions, we might look for information, theoretic signatures, patterns in particle behavior, or energy fluctuations that suggest data is being offloaded somewhere beyond our dimensions. Future quantum experiments or next-gen telescopes could stumble upon these fingerprints, revealing that wormholes aren't just space-time quirks, but the universe's original Wi-Fi network silently transmitting the codes of reality since the dawn of time. This theory doesn't just reshape how we see wormholes, it blurs the line between physics and information, suggesting the cosmos runs on a language we're only beginning to decipher. And if that's true, then the first wormhole travelers weren't explorers or engineers, they were the universe's own primal algorithms, racing through the void to assemble existence as we know it. What if the first wormholes weren't built to cross space but to conquer time? Imagine a civilization so advanced that the vast distances between stars meant nothing to them, because their true frontier wasn't the cosmos but the timeline itself. This is the spine-tingling premise behind the theory that wormholes could be relics of ancient time travelers, engineered not just to bridge galaxies but to stitch together epochs. The idea hinges on a radical possibility that some of the universe's earliest cosmic structures, anomalous galaxy alignments, unexplained energy signatures, even peculiar patterns in the cosmic microwave background, aren't accidents of nature, but fingerprints of a timeline-altering project older than Earth itself. The concept emerges from the strange marriage of general relativity and quantum mechanics. Einstein's equations have always allowed for the theoretical possibility of closed time-like curves, loops in spacetime that could enable travel into the past. But without a mechanism to create these loops, time travel remained a mathematical curiosity. Enter wormholes. If an ultra-advanced civilization could stabilize a wormhole, they might manipulate its endpoints so one mouth moves at relativistic speeds while the other remains stationary. Time dilation would then warp the two ends into different temporal coordinates, effectively turning the wormhole into a tunnel not just through space but through time. Picture a cosmic hourglass where the sand flows both ways, and someone or something might have walked through it long before stars lit up the universe. But why would a civilization build such a thing? The motives could range from the practical to the transcendent, perhaps to witness the birth of the cosmos firsthand, or to plant the seeds of their own existence through a paradox. Some theorists speculate that certain large-scale structures in the universe, like the mysterious Great Attractor pulling thousands of galaxies toward it, might not be natural gravitational anomalies but artifacts of deliberate temporal engineering. Imagine a time-traveling society arranging galaxies like dominoes, nudging cosmic evolution toward a desired outcome. The more unsettling variation, that we're seeing the aftermath of a temporal war where rival factions sculpted spacetime itself into strategic battlegrounds. The evidence, or lack thereof, might be hiding in plain sight. If ancient time travelers used wormholes to alter events, their interventions could have left scars in the fabric of reality. Subtle statistical improbabilities in the distribution of matter, inexplicably synchronized quasar emissions, or even the mysterious uniformity of the cosmic microwave background could all be the faint echoes of timeline manipulations. Some physicists have proposed that if such tampering occurred, it might be detectable through anomalies in quantum entanglement, as if particles separated by billions of light years remember being tampered with. This theory blurs the line between astrophysics and archaeology. If wormholes were time machines first and cosmic shortcuts second, then the universe isn't just a collection of objects, it's a palimpsest layered with the edits of civilizations we can't yet fathom. And if that's true, then the greatest discovery awaiting us might not be who's out there now, but who's been tampering with reality since before time had meaning. At the very edge of what we can measure, where spacetime itself shivers into quantum foam, lies a realm where the ordinary rules of physics dissolve. This is the Planck scale, where distances are so vanishingly small that space and time cease to behave as we know them. Here, in this subatomic storm, wormholes might flicker in and out of existence like bubbles in a boiling sea. These wouldn't be the grand, star-spanning tunnels of sci-fi dreams, but quantum wormholes, tiny, unstable, and governed by the bizarre laws of quantum gravity. Yet hidden in their fleeting existence could be the blueprint for something far greater, the universe's first natural wormholes waiting to be scaled up. To grasp just how small we're talking, imagine shrinking down until an atom looms like a galaxy. Now goes smaller, 1,000,000 billion times smaller. At the Planck length, spacetime isn't smooth or continuous. It's a frothing, fractal mess where wormholes could form spontaneously, linking distant points in a quantum blink. The catch: these tunnels would collapse almost instantly, far too brief and minuscule for even a photon to slip through. But what if they weren't meant to stay that way? Some theories suggest that in the extreme conditions of the early universe, where temperatures and energies dwarfed anything in today's cosmos, these Planck-scale wormholes might have been stretched, stabilized, or even woven together into larger structures by the universe's own explosive expansion. Think of it like cosmic origami. If spacetime is a sheet of paper crumpled at the smallest scales, then wormholes are the accidental folds where two distant points touch. An advanced civilization or even natural processes might have learned to smooth out those folds, reinforcing them into something traversable. The key lies in exotic physics, negative energy densities, quantum vacuum manipulations, or fields that no longer exist in our cooled-down universe. Some models even propose that dark energy, the mysterious force accelerating the universe's expansion, could be a remnant of whatever once inflated these tiny wormholes to usable sizes. The implications are staggering. If Planck-scale wormholes were scaled up, they wouldn't just connect space, they'd redefine it. A civilization mastering this tech wouldn't need to bend space-time. They could harvest the universe's innate quantum roughness, coaxing it into stable tunnels. The energy required would be beyond anything we can produce today, but the math doesn't forbid it. And if nature once did this naturally, the evidence might still be out there, hidden in the gravitational echoes of the Big Bang or the odd behavior of particles at quantum colliders. This idea flips the script on wormhole travel. Instead of building from scratch, we might just need to amplify what's already there, like turning whispers in the quantum static into a clear signal. The universe's first wormholes could have been born in this chaos, not as cosmic engineering projects, but as fundamental features of reality itself, waiting to be unlocked. And if they were, then the greatest shortcuts in existence might not be inventions, but discoveries buried in the fine print of spacetime since the dawn of time. The cosmic microwave background, that ancient afterglow of the Big Bang, has been called the universe's baby picture. But what if, hidden in its faint whispers, there's evidence not just of our universe's birth, but of countless others? Imagine wormholes not merely as shortcuts through space, but as bridges between realities, threading through the multiverse like stitches in a vast cosmic quilt. This isn't just speculative fantasy. Some physicists argue that anomalies in the CMB, those puzzling cold spots and strange asymmetries, might be scars left by primordial wormholes tugging our universe toward others in the multiverse. Think of the multiverse as an endless ocean, each universe a bubble rising from its depths. Normally, these bubbles remain forever separate, but wormholes could puncture the walls between them, creating temporary conduits for energy, information, or even matter to leak through. The math behind this is mind-bending. Quantum fluctuations in the early universe might have birthed not just our reality, but countless others, each with slightly different physical laws. Where these budding universes brushed against one another, spacetime could have stretched thin, forming wormholes' cosmic umbilical cords linking realities before they drifted apart. The most tantalizing clues lie in those odd CMB anomalies, the so-called cold spot. A vast region of unexpectedly low temperatures defies standard cosmic explanations. Some researchers suggest it could be the imprint of a long-vanished wormhole, a place where our universe once touched another, draining heat into a neighboring reality like water through a crack. Similarly, the mysterious hemispheric asymmetry, where one half of the sky shows subtle but statistically significant differences from the other, might hint at an ancient multiverse connection, a gravitational tug of war between our universe and its long-lost sibling. But how could such bridges persist? The answer may lie in the strange physics of inflation. During the universe's exponential expansion, wormholes linking parallel realities might have been frozen into space-time, their mouths stretched too far apart to collapse. Like a spider's silk hardening in the morning dew, these tunnels could have become fixed structures, their endpoints drifting into distant reaches of the multiverse. If so, the first travelers through them wouldn't have been ships or civilizations, but the fundamental forces themselves, bleeding between universes in the chaos of creation. This idea reshapes how we see the cosmos. If wormholes are multiverse conduits, then the anomalies we detect aren't just cosmic quirks, they're windows into realities beyond our own. Future telescopes mapping the CMB in unprecedented detail might find more of these scars, each a potential signpost to another universe. And if that's true, then the greatest journey humanity could undertake might not be across space, but through the veils separating existence itself, walking paths forged in the fire of creation by a multiverse we're only beginning to imagine. In the searing chaos of the universe's first moments, long before stars flickered to life, black holes may have formed in a way we can scarcely imagine today, not from collapsing stars, but directly from the dense, roiling energies of creation itself. These primordial black holes, some no heavier than an asteroid yet denser than a mountain, could have peppered the early cosmos like cosmic breadcrumbs. But what if they weren't scattered randomly? What if they were strung together like beads on an invisible necklace, connected by wormholes woven into the fabric of space-time? This is the radical idea that primordial black holes didn't just exist, they formed the universe's first highway system, a ready-made network of tunnels stitching the cosmos together before the first galaxies even took shape. The theory hinges on the extreme conditions of the early universe, where quantum fluctuations and phase transitions could have birthed black holes in vast numbers. Unlike the black holes we observe today, forged in stellar explosions, these primordial variants might have carried unique properties, some spinning at near light speeds, others threaded with cosmic strings or exotic matter. General relativity tells us that rapidly rotating black holes can twist spacetime around them, forming structures known as ergospheres. If two such black holes orbited each other, their ergospheres might have twisted spacetime into a bridge between them, a natural wormhole stabilized by their mutual motion. Picture two whirlpools spinning in a cosmic bathtub. Their vortices could momentarily connect, creating a fleeting passage before snapping back into place. But here's where the idea gets electrifying. If enough primordial black holes formed in close proximity, their collective gravitational dance might have woven an entire web of these tunnels, a sprawling subway system threading the infant universe. Advanced civilizations wouldn't need to build wormholes, they'd just need to chart the network, navigating these pre-existing shortcuts like cosmic spelunkers. The energy required to traverse them could have been far less than creating new wormholes from scratch. Some models even suggest that dark matter, currently one of astronomy's greatest mysteries, might be composed partly of these ancient black holes, their invisible gravity still shaping the cosmos while their wormhole connections lie dormant, waiting to be rediscovered. Evidence for this audacious theory might already be hiding in the sky. Primordial black holes, if they exist, could explain puzzling gravitational lensing events where distant stars briefly brighten without any visible cause. More tantalizingly, certain black hole mergers detected by gravitational wave observatories exhibit peculiar spin rates or mass ratios that don't quite match predictions, hinting at an exotic origin. If future observations uncover black holes that seem too small, too old, or too numerous for conventional theories, we might be glimpsing the remnants of this primordial subway, its stations long abandoned but its tunnels still intact. The implications rewrite our cosmic history. If wormholes linked the first black holes, then the universe's earliest large-scale structures weren't just clumps of gas, they were interconnected nodes in a vast, ancient transit system. Matter and energy could have flowed through these tunnels, redistributing mass in ways that seeded galaxy formation or even influenced the universe's expansion. The first travelers might not have been civilizations at all, but raw particles or bursts of energy funneled through spacetime's hidden plumbing long before the first stars flickered on. This idea blurs the line between astrophysics and archaeology. Finding these primordial wormholes wouldn't just confirm a wild theory, it would unveil the universe's original infrastructure, a ghostly roadmap etched into reality at the dawn of time. And if we ever learn to reactivate them, humanity might not be building the future's highways. We'd simply be reopening roads that were paved for us billions of years before we existed. Empty space isn't really empty. Even in the deepest void between galaxies, there's a seething, invisible ocean of energy quantum foam, where particles and forces flicker in and out of existence in a dance dictated by the universe's fundamental laws. These vacuum fluctuations might seem too ephemeral to matter, but they're powerful enough to warp spacetime itself. And in the extreme conditions of the early universe, that warping could have forged something extraordinary, spontaneous wormholes erupting from the quantum chaos like cosmic geysers. The mechanism is as elegant as it is mind-bending. At the quantum scale, pairs of virtual particles constantly pop into existence, borrowing energy from the vacuum before annihilating each other in a flash. Normally, this happens far too quickly to leave any trace, but in the universe's first moments, when energies were unimaginably high, these fluctuations might have been powerful enough to twist spacetime into microscopic tunnels. Picture a roiling pot of water. Most bubbles vanish instantly, but under the right conditions, some merge and grow. Similarly, a rare few quantum wormholes might have escaped annihilation, stabilized by the sheer density of energy around them. What's startling is that these vacuum-borne wormholes wouldn't need exotic matter or advanced engineering to stay open, at least not initially. The inflationary expansion of the universe could have stretched them to macroscopic sizes, freezing them into spacetime like wrinkles in a rapidly inflated balloon. Some models suggest that dark energy, the mysterious force accelerating cosmic expansion today, might be a remnant of this process, a cosmic fossil hinting at when spacetime itself was malleable enough to sprout tunnels naturally. The implications are staggering. If vacuum fluctuations spawned wormholes in the early universe, they might still lurk all around us, too small or diffuse to detect with current technology. But under the right conditions, perhaps in the intense gravitational fields near neutron stars or in high-energy particle collisions, we might just coax them back into visibility. Experiments with quantum entanglement or precision measurements of gravitational waves could reveal subtle anomalies pointing to these hidden structures. This theory flips the script on wormhole creation. Instead of imagining civilizations laboring to build them, the universe might have offered them freely, a cosmic lottery where a lucky few quantum fluctuations hit the spacetime jackpot. And if that's true, then the greatest shortcuts in existence weren't engineered, they were grown like wildflowers in the cracks of reality. When gravitational waves were first detected in 2015, they confirmed a century-old prediction that cataclysmic events like black hole collisions send ripples through spacetime itself. But what if those ripples aren't just cosmic echoes? What if, under the right conditions, they could twist spacetime into something far more extraordinary, fleeting wormholes, flickering into existence for mere fractions of a second before dissolving back into the void? This is the provocative idea that some of the universe's most violent events might not just distort spacetime, they could momentarily stitch it together, creating portals too brief for starships, but perhaps not for information, energy, or even beings we can't yet imagine. The physics behind this is as elegant as it is strange. When two black holes spiral inward and collide, they don't just warp spacetime, they send it ringing like a struck bell, with gravitational waves radiating outward at light speed. But buried in the math is a lesser-known possibility. The collision's sheer violence could pinch spacetime so severely that it momentarily forms a tunnel, a wormhole bridging the black hole's original locations. Picture two whirlpools in a cosmic ocean merging into one. For an instant, their depths might connect before the water crashes back to equilibrium. Similarly, a black hole merger could tether the 2 points in space, not with a permanent bridge, but with a wormhole that flashes in and out of existence too quickly for even light to traverse. The question isn't just whether these tunnels form, but whether they could ever be harnessed. The energy scales involved are beyond anything human technology could muster, but not necessarily beyond the reach of a sufficiently advanced civilization. Imagine a species that could predict black hole mergers with pinpoint accuracy. Positioning probes or relays near the collision points to catch the wormhole's brief opening. Like cosmic surfers riding a wave, they might send pulses of information or quantum-entangled particles through these tunnels, transmitting data across galaxies in the blink of an eye. Even more intriguing, if the wormholes in points were carefully manipulated, perhaps using gravitational lensing or exotic matter, their lifespans might be stretched just enough to allow traversal. Clues to this audacious idea might already exist in the gravitational wave data we've collected. LIGO and Virgo have detected dozens of mergers, each with a unique waveform, a fingerprint of the event's physics. If even a handful of these collisions produced transient wormholes, their signatures could be hiding in anomalies buried in that data, unexpected echoes, frequency shifts, or delays in the gravitational wave signals. Some theorists speculate that certain glitches in observed mergers might hint at spacetime briefly folding in ways our models don't yet account for. Future detectors like the space-based LISA observatory could catch even fainter whispers of these phenomena, potentially uncovering wormholes that formed not just from black holes, but from the collisions of neutron stars or other extreme cosmic events. The implications rewrite how we view gravitational waves. Instead of just cosmic noise, they might be the universe's most energetic construction crews briefly assembling tunnels before vanishing into the dark. And if ancient civilizations ever learned to read these ripples well enough to hitch a ride, the first interstellar messages might not have been sent through space, but threaded through the echoes of colliding stars. We could be surrounded by the remnants of these fleeting shortcuts, their builders long gone, but their passageways still flickering in the daylight, waiting for us to decode them. Neutrinos are the universe's ultimate ghosts, particles so tiny and elusive that trillions pass through your body every second without a single interaction. They barely notice matter exists, and matter barely notices them. But in the extreme energies of the early cosmos, these nearly massless phantoms might have been far more than passive bystanders. They could have been cosmic architects sculpting spacetime itself into tunnels we now call wormholes. The theory hinges on neutrinos' bizarre properties. Unlike other particles, they interact so weakly with matter that they can traverse entire planets or stars without slowing down. In today's universe, this makes them nearly impossible to catch. But in the first seconds after the Big Bang, neutrinos weren't just abundant. They were among the most powerful forces in existence, flooding the cosmos at energies we can't recreate even in our mightiest particle colliders. At these scales, their weak interactions might have taken on a strange new role. Imagine spacetime as a calm sea, and neutrinos as trillions of microscopic torpedoes ripping through it. Under normal conditions, their wakes vanish instantly, but in the early universe's dense, hot plasma, those ripples could have piled up, amplifying like waves in a storm until they warped spacetime into tiny wormholes spun from sheer kinetic chaos. What's even wilder is that neutrinos might not just create wormholes, they could reveal them. Today, when ultra-high-energy neutrinos streak across the cosmos, they occasionally interact with matter, producing faint bursts of light or particle showers. But some of these neutrinos arrive with energies so extreme that their origins defy explanation. One tantalizing possibility: they took a shortcut. If a neutrino's path intersected with a primordial wormhole, it might have slipped through, crossing unimaginable distances in a blink. We'd detect it as an outlier, a particle seemingly too energetic to have traveled the long way without losing steam. These ghost travelers could be the universe's way of highlighting hidden tunnels, pointing us toward structures we'd never see otherwise. The hunt for evidence is already underway. IceCube, the giant neutrino observatory buried in Antarctic ice, has detected a handful of these ultra-high-energy neutrinos with no clear source. While most are likely from black holes or supernova, a few exhibit odd trajectories or energy signatures that don't quite fit. Could these be the echoes of ancient wormholes, their passageways long vanished but their fingerprints still etched into the particles that slipped through? Future detectors like the planned IceCube Gen 2 might catch enough of these outliers to map patterns, clusters of neutrinos arriving from seemingly nowhere, all hinting at the same invisible tunnels in spacetime. This idea flips our understanding of wormholes on its head. Instead of being monumental structures built by civilizations or forged in black hole collisions, they might be fleeting, natural phenomena, spun up by particles we barely understand, then dissolving back into the quantum foam. And if that's true, then the universe's first wormhole travelers weren't explorers or engineers. They were ghosts slipping through the cracks of reality before anyone knew the cracks were there. Plasma isn't just the stuff of stars, it's the universe's original building block, a seething sea of charged particles that filled the cosmos long before atoms ever formed. In those first fiery moments after the Big Bang, this plasma didn't just drift aimlessly. It whirled and churned like a cosmic hurricane, sculpted by unimaginable magnetic fields. And within that chaos, something extraordinary might have taken shape. Vast, spinning vortexes of plasma so powerful they didn't just bend space-time. They twisted it into knots, forging wormholes in the furnace of creation itself. Picture a tornado made of pure energy, its winds streaming with particles moving at near light speeds. Now imagine that tornado isn't just spinning through space, it's spinning space, coiling the fabric of reality around it like thread on a spindle. Under normal conditions, these vortexes would eventually dissipate, But in the early universe's extreme magnetic fields, they could have grown so intense that spacetime itself buckled under the strain, forming tunnels where the vortex's top and bottom met. Think of it like twisting a rubber band until the ends touch, except here, the rubber band is the universe and the point of contact is a wormhole, a shortcut through the cosmic storm. The math behind this is as dazzling as the concept. Plasma physicists have long known that when charged particles spiral in powerful magnetic fields, they generate currents capable of warping spacetime in ways ordinary matter can't. In laboratories, we've seen tiny versions of this pinches of plasma creating brief, microscopic distortions. Scale that up to the cosmic conditions of the early universe, where magnetic fields were billions of times stronger, and those distortions could have become self-sustaining, held open by the very forces that birthed them. Some models even suggest these plasma wormholes wouldn't need exotic matter to stabilize them. The swirling currents themselves might act as a kind of dynamic scaffold, constantly replenishing the tunnel's structure like a whirlpool that never collapses. But how would we ever detect such ephemeral structures? The answer might lie in the cosmic microwave background. If plasma vortexes did twist spacetime into wormholes, the energy released as those tunnels formed and collapsed would have left imprints in the universe's oldest light, subtle swirls or concentric ripples hidden in the CMB's faint glow. Astronomers have already spotted puzzling anomalies in this radiation, patterns that defy conventional explanations. Could these be the fossilized signatures of primordial plasma whirlpools, their once violent rotations frozen into the sky like cosmic fingerprints? Even more intriguing is the idea that these vortexes might not be relics of the past. In the hearts of quasars or the accretion disks of supermassive black holes, similar conditions could arise, plasmas spinning at blistering speeds under crushing magnetic fields. If a wormhole formed in such an environment today, it might flare briefly like a cosmic flare, detectable as a sudden burst of high-energy particles or gravitational waves with a peculiar spiral signature. Some theorists speculate that certain fast radio bursts, those enigmatic milliseconds-long blasts of radio waves from deep space, could be the death cries of these plasma-born wormholes, their collapse sending shockwaves through the fabric of reality. This theory doesn't just offer a new way to imagine wormholes, it ties them to the universe's most fundamental forces. If plasma vortexes can twist spacetime into tunnels, then the cosmos might be threaded with shortcuts we've overlooked simply because we weren't looking for the right clues. And if that's true, then the first travelers through these wormholes weren't ships or particles, they were storms, hurling themselves through the universe's tangled seams long before the first stars learned to shine. At the frontier of theoretical physics lies one of the most elegant frameworks ever conceived: supersymmetry, a theory so beautiful it could rewrite our understanding of reality itself. This grand idea proposes that every particle we know has a hidden twin, a super partner with properties just different enough to solve some of the universe's deepest mysteries. But here's where things get truly cosmic. These undiscovered particles might hold the key to stabilizing wormholes, transforming them from fleeting mathematical curiosities into traversable cosmic highways. If supersymmetry is real, then nature may have baked the recipe for interstellar travel right into the fabric of existence, waiting to be uncovered. The magic lies in the unique properties of these theoretical superpartners. Unlike ordinary matter, some supersymmetric particles could carry negative energy densities or exhibit gravitational repulsion, precisely the exotic qualities needed to prop open a wormhole's throat against its natural tendency to collapse. Picture a tunnel with walls made of rubber bands constantly trying to snap shut. Now imagine lining those walls with springs that push outward instead. That's what certain superpartners might do to spacetime, counteracting the crushing force of gravity with their own peculiar physics. The lightest of these particles, the neutralino, could be particularly revolutionary. As a leading candidate for dark matter, it might already permeate the cosmos, invisible and abundant, a natural resource for stabilizing wormholes without any advanced engineering at all. What makes this theory so tantalizing is its connection to the early universe. During the first moments after the Big Bang, when energies reached unimaginable levels, supersymmetry would have been in full bloom, with superpartners emerging as commonly as ordinary particles do today. In that seething primordial soup, spacetime itself might have been crisscrossed with temporary wormholes, stabilized by the fleeting presence of these exotic particles. Some models suggest that as the universe cooled and supersymmetry broke down, its particles becoming too massive to form, most of these tunnels collapsed. But a rare few, threaded with just the right configuration of superpartners, could have survived like cosmic fossils, frozen in place by the very physics that once made them possible. The implications are staggering. If supersymmetric wormholes exist, they wouldn't just be artifacts of some ancient civilization's technology. They'd be natural features of the universe, as fundamental as black holes or neutron stars. Finding them might not require scanning for alien megastructures, but rather detecting the faint gravitational whispers of their unique particle signatures. Experiments at the Large Hadron Collider are already hunting for superpartners, while telescopes scour the cosmos for anomalies that could hint at their presence. A single confirmed detection would do more than validate decades of theoretical work. It could unveil a hidden network of tunnels, woven into reality by the same symmetry that governs everything from quarks to galaxies. This idea blurs the line between astrophysics and alchemy. If supersymmetry holds the secret to stable wormholes, then the universe's first travelers might not have needed technology to traverse the stars. They could have simply harnessed particles we're only beginning to dream of. And if we ever confirm their existence, humanity might not be inventing the future's transportation network, but rediscovering a gift left for us in the fine print of creation itself. Our universe might be far stranger than we ever imagined, not just a vast expanse of three-dimensional space, but one thin slice of a higher dimensional reality, floating like a sheet of paper in a cosmic stack. This is the brain world scenario, a mind-bending idea from string theory that suggests our entire cosmos exists on a membrane or brain, drifting through a higher dimensional space called the bulk. And if that's true, then the most dramatic events in cosmic history might not have happened within our universe at all, but between universes when two brains collided like symbols in the dark, sending shockwaves through reality that could have birthed the first wormholes in existence. Picture two soap bubbles drifting toward each other in slow motion. When they touch, their surfaces ripple violently before merging or rebounding. Now imagine those bubbles are entire universes, and their collision isn't just a meeting of membranes, it's a cataclysm powerful enough to puncture spacetime itself. According to certain string theory models, such an impact wouldn't just create a bang. It could tear open tunnels between brains, wormholes threading through the bulk like stitches holding the fabric of the multiverse together. These wouldn't be the delicate quantum wormholes we've imagined before, but massive primordial structures forged in the furnace of interdimensional chaos. The physics behind this is as elegant as it is speculative. In the brain world scenario, gravity, unlike other forces, isn't confined to our brain. It leaks into the bulk, which means when two brains collide, their gravitational interactions could twist higher dimensional spacetime into shapes we can barely visualize. Some calculations suggest that the energy released in these collisions might form not just one wormhole, but an entire network of cosmic capillaries linking brains across dimensions. The most striking part, these tunnels wouldn't need exotic matter to stay open. The higher dimensional geometry itself could stabilize them, like a straw punched through multiple layers of a cake, its structure held firm by the surrounding bulk. But here's the haunting question. If brain collisions created wormholes, where do they lead? Some theories suggest they might connect parallel universes with slightly different physical laws, allowing matter or energy to bleed between realities. Others propose that certain black holes in our universe, especially those with unexplained properties, might actually be the mouths of these primordial brain-borne tunnels, their other ends anchored to distant brains or even different eras in time. The most provocative idea, that the Big Bang itself was the result of a brain collision, meaning the first wormholes might not just predate our universe, they could have helped birth it, funneling energy and structure into the newborn cosmos like umbilical cords feeding a star. Evidence for this wild idea is frustratingly scarce but not impossible to find. If brain collisions left wormholes in our universe, they might betray their presence through subtle gravitational anomalies, regions where space-time curves in ways that defy conventional explanations. Certain mysterious voids in the cosmic web where galaxies seem suspiciously sparse could be the scars of ancient wormholes diluting matter across dimensions. Even the cosmic microwave background might hold clues, odd temperature fluctuations or polarization patterns that hint at spacetime being tugged by higher dimensional structures. This theory doesn't just redefine wormholes, it reshapes our place in the cosmos. If brain collisions forged the first tunnels, then interstellar travel might one day mean navigating not just space, but the hidden dimensions that envelop it. The ultimate highways wouldn't lie within our universe, but through the cracks between realities, a subway system strung through the bulk by collisions that happened long before stars or galaxies even existed. And if that's true, then the first wormhole travelers might not have been beings at all, but universes themselves brushing against each other in the dark and leaving behind doorways we're only beginning to dream of opening. Quantum entanglement is one of the most baffling phenomena in physics, particles separated by vast distances instantaneously influencing each other's states, as if space and time between them simply don't exist. Einstein famously called it spooky action at a distance, but what if that spookiness isn't just a quirk of quantum mechanics? What if entangled particles are literally connected, not by some invisible force, but by something far more tangible? Microscopic wormholes threading through the fabric of spacetime like cosmic stitching. This radical idea, known as the ER=EPR conjecture, suggests that entanglement and wormholes might be two sides of the same coin, bridges so small they're hidden in the quantum noise, waiting to be scaled up. The theory originates from a stunning convergence of two seemingly unrelated concepts. In 1935, Albert Einstein and Nathan Rosen proposed wormholes, Einstein-Rosen bridges, as mathematical solutions to general relativity. That same year, Einstein, Rosen, and Boris Podolsky highlighted the bizarre nature of quantum entanglement in their famous EPR paradox. Decades later, physicists Leonard Susskind and Juan Maldacena noticed something uncanny. The equations describing entangled particles and those governing wormholes bore an eerie resemblance. It was as if the universe had left a clue that these phenomena weren't just analogous, they were fundamentally the same. Picture two entangled particles not as separate objects, but as the mouths of a wormhole so tiny it's curled up at the Planck scale, their connection literally folded through a higher dimension. But how could something so small ever become a traversable tunnel? The key lies in scaling. Just as a quantum fluctuation in the early universe might have been stretched into a macroscopic wormhole by cosmic inflation, entangled particles could, in theory, have their hidden bridges expanded. The process would require harnessing exotic physics, injecting negative energy to stabilize the wormhole's throat, then carefully manipulating quantum fields to stretch it without breaking the entanglement. Think of it like pulling apart a pair of magnets connected by an invisible rubber band. At first, the band is slack, undetectable, but with enough precision and energy, you might stretch it into something tangible. Some models suggest that advanced civilizations could use quantum teleportation protocols as blueprints, gradually knitting microscopic wormholes into larger structures by entangling massive particles or even macroscopic objects. The implications rewrite the rules of interstellar travel. If entanglement is wormhole formation in its most basic form, then the universe has already provided the raw materials for a galactic transit system. We just need to learn how to assemble them. Labs around the world are already probing this idea, experimenting with entangled particles to search for anomalies in their behavior that might hint at hidden spacetime structures. In 2023, a team at Google's Quantum AI lab observed peculiar correlations in entangled qubits that some theorists argue could align with microscopic wormhole dynamics. It's a controversial interpretation, but if even partially correct, it would mean the first steps towards scalable wormholes aren't happening in particle colliders or space telescopes, but in quantum computers humming quietly on Earth. This idea blurs the line between physics and philosophy. If every entangled pair in the universe is secretly linked by a wormhole, then spacetime might be far more interconnected than we ever imagined, a vast, invisible web of tunnels humming beneath the surface of reality. The first wormhole travelers wouldn't need to carve new paths through the cosmos. They'd only need to trace the threads that are already there, pulling at quantum seams until the universe unravels its oldest shortcuts right before their eyes. Dark energy is the universe's greatest unsolved riddle, an invisible force stretching spacetime apart faster and faster, driving galaxies away from each other as if reality itself were coming unstitched. Yet within this relentless expansion might lie an unexpected cosmic gift, wormholes not crushed by the universe's growth but forged by it. Imagine spacetime not just as an expanding sheet, but as a taffy-like fabric being pulled in all directions. In the early universe, when dark energy's grip was strongest, that stretching could have thinned spacetime until it tore in places, not random rips but precise, self-reinforcing tunnels, threaded through the cosmos like capillaries in an ever-growing body. The mechanics are as counterintuitive as they are elegant. Normally, expansion would seem to weaken spacetime, making wormhole formation less likely. But dark energy doesn't just stretch the cosmos, it warps the very rules governing it. During inflation, the universe's exponential growth could have amplified quantum fluctuations into macroscopic structures, including wormholes. Dark energy's modern acceleration is far gentler, but in those first moments, its explosive push might have twisted spacetime into configurations that outlasted inflation itself. Picture a balloon inflating so rapidly that tiny imperfections in its surface don't smooth out, they crystallize into permanent folds. Wormholes could be those folds, frozen into the universe's architecture before spacetime had time to settle. What's especially tantalizing is that dark energy's repulsive force might have done more than create these tunnels. It could have stabilized them. Traditional wormholes collapse under their own gravity, but dark energy behaves like anti-gravity, pushing outward. If a wormhole formed during inflation, dark energy's pressure could have countered the crushing force, holding the throat open just long enough for particles or energy to slip through. Some models even suggest these tunnels would have been self-sustaining, their ends carried apart by expansion while the throat remained intact, like a cosmic tether stretched but never snapped. The best evidence might lie in the universe's large-scale structure. If dark energy stretched spacetime into wormholes, matter wouldn't have distributed evenly. It would have funneled through these tunnels, creating faint but detectable patterns. Astronomers have observed bizarre filamentary structures in the cosmic web, strands of galaxies stretching across voids with no clear explanation. Could these be the echoes of ancient wormholes, their gravitational influence guiding matter like rivers carved by long-vanished glaciers? Even more intriguing are the so-called dark flows, mysterious, coordinated motions of galaxy clusters that suggest something beyond the observable universe is tugging at them. Wormholes formed during inflation could stretch beyond our cosmic horizon, their distant ends pulling matter in ways that defy conventional models. This idea flips dark energy from a destructive force into a potential architect of cosmic infrastructure. Instead of seeing the universe's expansion as a barrier to interstellar travel, It might be the very process that built the highways threading spacetime with tunnels while the cosmos was still young and malleable. If true, then the first wormhole travelers weren't ships or civilizations, but particles and forces, riding the universe's own explosive growth to places we can't yet see. And if remnants of those tunnels linger, hidden in the voids between galaxies, then dark energy isn't just tearing the cosmos apart. It might have left us a map written in the wrinkles of spacetime itself. Neutron stars are the universe's ultimate pressure cookers, stellar corpses so dense that a teaspoon of their material would weigh 1 billion tons on Earth. When two of these cosmic extremes spiral toward each other, their collision unleashes energy on a scale that defies imagination. But beyond the dazzling bursts of gamma rays and gravitational waves, these mergers might pull off an even more astonishing feat, twisting spacetime into the first stable wormholes the cosmos has ever known. The physics at play here is nothing short of spectacular. As neutron stars circle each other in their final death spiral, their immense gravity distorts spacetime into extreme shapes. Unlike black holes, which hide their inner workings behind event horizons, neutron stars are bare laboratories of extreme physics, their surfaces visible, their tidal forces stretching and compressing spacetime like putty. When they finally collide, the impact doesn't just create a black hole. It momentarily warps the surrounding spacetime into a structure so contorted that theoretical models suggest it could pinch into a wormhole. Picture two whirlpools merging in a cosmic ocean, their combined spin twisting the water into a temporary tunnel between them. Now replace the water with spacetime itself, and you've got the essence of a neutron star merger's hidden potential. What makes these wormholes uniquely promising is their potential stability. While black hole collisions might form fleeting tunnels, neutron star mergers have two critical advantages. First, their matter-rich environment floods the surrounding space with exotic particles, quark, gluon plasma, strange matter, and other high-energy byproducts that could act like cosmic mortar, reinforcing the wormhole's throat against collapse. Second, the intense magnetic fields generated during the merger, trillions of times stronger than Earth's, could thread the wormhole with stabilizing forces, much like steel cables buttressing a tunnel's walls. Some simulations even suggest that certain configurations could produce wormholes that last for milliseconds, an eternity in particle physics terms, and just long enough for information or energy to traverse them. The smoking gun for this theory might lie in the aftermath of observed mergers. When LIGO detected the first neutron star collision in 2017, the event didn't just produce gravitational waves. It also emitted a kilonova, a brilliant flash of light rich in heavy elements like gold and platinum. But hidden in that data were peculiar anomalies, a fraction of the gravitational wave signal arriving slightly delayed, and certain high-energy particles appearing to echo as if they'd taken a detour through folded spacetime. While these could be random noise, some theorists argue they align eerily well with predictions of a wormhole's brief existence during the merger's chaos. Future observations with more sensitive detectors could look for these telltale hiccups in the gravitational waveform, subtle fingerprints of spacetime momentarily stitching itself into a shortcut. Perhaps the most breathtaking implication is that nature might have been building wormholes all along, long before civilizations could dream of them. If neutron star mergers naturally produce even transient tunnels, then the universe's first stable wormholes might not be artificial constructs, but cosmic accidents, byproducts of the most violent dances in existence. And if that's true, then the remnants of these events could still linger, scattered across the cosmos like forgotten doors, waiting for someone or something to turn the key. Quantum tunneling is one of the strangest behaviors in the subatomic world. A particle suddenly appearing on the other side of an impossible barrier, as if it blinked out of existence and rematerialized somewhere new. Normally, this phenomenon is confined to tiny scales, like electrons hopping through solid walls. But what if this quantum magic isn't just a microscopic quirk? What if, under the right conditions, particles don't just tunnel through barriers, they tunnel through spacetime itself, stitching together wormholes in their wake? At the heart of this idea lies a radical reimagining of how quantum mechanics and gravity might interact. In conventional physics, particles tunnel because their wave functions. The probability clouds defining their positions extend slightly beyond barriers they shouldn't be able to cross. It's like rolling a ball up a hill so steep it should roll back, only for the ball to inexplicably appear on the other side. Now replace the hill with spacetime itself and the ball with a particle's entire mass. If a particle's quantum field fluctuates violently enough, it could momentarily warp spacetime into a bridge between 2 points, effectively creating a wormhole just wide enough for the particle to traverse. Picture a needle punching through folded fabric, leaving behind a tiny thread where the hole briefly held open. The key here is energy. Quantum tunneling typically involves particles slipping through barriers they lack the classical energy to overcome. But in extreme environments like near a black hole's event horizon or in the searing aftermath of the Big Bang, particles could tap into spacetime's own quantum fluctuations, borrowing energy from the vacuum itself to forge tunnels through the cosmic fabric. Some models suggest that high-energy particles colliding in particle accelerators might already be producing ephemeral wormholes this way, their existence hidden in the statistical noise of experiments. If true, it would mean the universe's smallest particles have been quietly engineering spacetime shortcuts all along, too fleeting for us to notice until now. This theory flips the script on wormhole formation. Instead of requiring vast amounts of exotic matter or cosmic-scale engineering, traversable wormholes might emerge naturally from quantum processes we're only beginning to understand. Imagine an advanced civilization not building wormholes, but coaxing them into existence, nudging particles into just the right configurations to let spacetime tunnel itself. The implications ripple across physics. If quantum tunneling can birth wormholes, then the universe might be far more interconnected than we ever guessed, its fabric threaded with infinitesimal tunnels humming in the quantum static. Detecting these particle-scale wormholes wouldn't require telescopes, but ultra-precise quantum experiments. Subtle anomalies in entangled particles' behavior, unexpected energy shifts in high-energy collisions, or even peculiar delays in quantum teleportation protocols could hint at spacetime momentarily pinching into tunnels. Some theorists argue that certain results from the Large Hadron Collider, like anomalous particle scattering angles, might already be whispers of this phenomenon, buried in data we haven't fully deciphered. Future quantum sensors designed to probe spacetime's granularity could finally catch these wormholes in the act, revealing a universe where the line between particle physics and cosmic engineering blurs into something extraordinary. The most poetic part: if quantum tunneling can spawn wormholes, then the universe's first interstellar travelers weren't ships or civilizations, but particles themselves hopping between stars via spacetime's hidden backdoors, stitching the cosmos together one quantum leap at a time. And if we ever learn to harness this, humanity might not conquer the stars by building rockets, but by listening to the universe's quietest, oldest trick, tunneling through the impossible. Magnets, as we know them, always come with two inseparable poles, north and south, forever bound together no matter how many times you break them apart. But what if nature allowed something radically different? Enter magnetic monopoles, hypothetical particles that carry just a single magnetic charge, either north or south, untethered from their opposite. These elusive entities aren't just curiosities for physicists. They could be cosmic keystones, holding open the universe's most stable wormholes like invisible pillars propping up spacetime tunnels. The connection between monopoles and wormholes emerges from their shared exotic physics. Ordinary matter struggles to counteract the crushing gravity that slams wormholes shut, but a monopole's peculiar electromagnetic fields could generate repulsive forces powerful enough to keep a tunnel's throat open. Picture a wormhole as a collapsing hallway. Monopoles would line its walls like magnetic scaffolding, their one-sided fields pushing outward with enough energy to counterbalance the inward pull of spacetime itself. The math behind this is startlingly elegant. General relativity and quantum theory both hint that monopoles, if they exist, would warp spacetime in ways that align perfectly with wormhole stabilization. Some equations even suggest a single monopole could anchor an entire wormhole network, threading the cosmos with tunnels where their magnetic lines converge like subway lines meeting at a central hub. Where could these spacetime architects be hiding? Theories point to the universe's earliest moments. During the phase transitions following the Big Bang, symmetry-breaking events might have forged monopoles as topological defects. Think of them as cosmic cracks frozen into the fabric of reality. While most models predict they'd be absurdly rare today, some monopoles could have survived, lurking in the depths of galaxy clusters or even trapped inside neutron stars. Their sheer density, with masses potentially 1 trillion times heavier than a proton, means one monopole could pack enough punch to stabilize a wormhole for millennia. If an advanced civilization ever learned to harvest or synthesize them, they'd possess the ultimate toolkit for interstellar travel. The hunt for monopoles is already underway. Experiments deep underground, shielded from cosmic noise, search for their faint ionization trails. Others scrutinize lunar rocks for traces of monopole impacts over billions of years. But the most tantalizing clues might lie in the skies. Certain pulsars spinning neutron stars with lighthouse-like radio beams show inexplicable frequency shifts that some theorists argue could stem from monopoles altering their magnetic fields. Even more intriguing are anomalies in cosmic rays, where ultra-high-energy particles arrive with signatures that resemble magnetic shadows of something massive passing through interstellar space. This idea transforms how we imagine wormhole engineering. Instead of needing vast quantities of exotic matter, a handful of monopoles might suffice. Nature's own spacetime stabilizers forged in the Big Bang's fires. If they're out there waiting to be found, the universe's most durable shortcuts might not be inventions but discoveries, threaded with the same particles that once helped shape the cosmos itself. Black holes have long been considered cosmic dead ends, places where matter and energy vanish forever behind an inescapable curtain of gravity. But Stephen Hawking's revolutionary work revealed they aren't quite the eternal prisons we once imagined. They leak through a bizarre quantum quirk. Black holes slowly evaporate, emitting a faint hiss of particles now called Hawking radiation. Yet what if this evaporation isn't just random quantum noise? What if each escaping particle is a clue, a whisper from hidden tunnels threading through spacetime itself? The conventional view of Hawking radiation paints it as a lonely process, particles spontaneously appearing near a black hole's event horizon, with one falling in while the other escapes, draining the black hole's energy over eons. But some theorists propose a far more intriguing possibility. These particles might not be emerging from empty space at all. Instead, they could be surfacing through microscopic wormholes, quantum shortcuts linking the black hole's interior to distant points in the universe. Imagine a black hole not as a one-way chute, but as a tangled knot of spacetime threads, with particles occasionally slipping through the loosest fibers. This idea hinges on the strange geometry of black holes. Near the event horizon, spacetime bends so severely that quantum fluctuations could pinch off into self-contained loops, wormholes too small to see, but large enough for particles to traverse. As Hawking radiation escapes, it might carry subtle fingerprints of these hidden tunnels, slight delays in emission, unexpected correlations between particles, or energy signatures that defy standard models. Some calculations even suggest that if wormholes are involved, the radiation spectrum wouldn't be perfectly thermal. It would bear the statistical marks of particles having taken detours through folded spacetime. The implications ripple across astrophysics. If Hawking radiation is wormhole-tinged, then black holes might not destroy information after all. They could be funneling it elsewhere, preserving it in a form we're only beginning to decode. This could solve the infamous black hole information paradox, not by rewriting quantum mechanics, but by revealing that the universe has been quietly routing data through backdoors all along. Even more tantalizing is the thought that advanced civilizations might have learned to read this radiation, treating evaporating black holes as cosmic message boards broadcasting signals through spacetime's hidden seams. The hunt for evidence is already underway. Next-generation telescopes designed to study the faintest emissions from primordial black holes could look for anomalies in their evaporation patterns. Certain particle detectors tuned to catch ultra-high energy Hawking-like radiation might spot the telltale statistical quirks of wormhole-mediated decay. If nature's most enigmatic objects are secretly threaded with tunnels, then the answers, and perhaps the universe's oldest roads, are written in the light they leave behind as they fade into the dark. String theory proposes a cosmos far stranger than the three dimensions we experience, a universe humming with extra dimensions, curled up so tightly we've never noticed them. These hidden folds in reality aren't just mathematical curiosities. They might be the universe's original wormhole network, offering shortcuts through higher dimensional space that bypass our familiar laws of physics entirely. Imagine trying to walk from one side of a paper to the other by trudging across its length until you realize you can fold the paper, punching through to the other side in an instant. That's the essence of how extra dimensions could rewrite the rules of interstellar travel, turning impossible journeys into mere hops through the cosmic origami of spacetime. The math behind this is breathtaking. In string theory's framework, the universe could have 10 or 11 dimensions, with all but our familiar 3 spatial dimensions compactified, curled into loops smaller than an atom. But under extreme conditions near black holes during cosmic inflation or in the searing heat of the early universe, these dimensions might have briefly unfurled, creating bridges between distant points in our 3-dimensional space. Picture a garden hose lying on the ground. From a distance, it looks one-dimensional like a line, but up close you see its surface is a 2-dimensional cylinder wrapped around a hidden dimension. Wormholes in string theory could work similarly, threading through these higher dimensional back alleys where distances contract and physics bends to new rules. What makes this idea so electrifying is how it solves wormholes' biggest hurdles. In our 3-dimensional world, stabilizing a wormhole requires unimaginable amounts of exotic matter. But in higher dimensions, the geometry itself could provide stability. Just as a straw's cylindrical shape holds its form better than a flat piece of paper, a wormhole woven through extra dimensions might stay open naturally, its structure reinforced by the multidimensional fabric it's built from. Some string theory models even suggest these tunnels wouldn't just connect 2 points in our universe, they might link to entirely separate brain worlds, parallel universes floating in the higher dimensional bulk like sheets in a cosmic stack. The first travelers through these higher dimensional shortcuts wouldn't have needed spaceships or technology, they might have been fundamental strings themselves, the vibrating threads that string theory says make up all matter. In the early universe's extreme energies, strings could have stretched across extra dimensions like spider silk, weaving transient wormholes as they went. Over time, as the cosmos cooled and extra dimensions collapsed, these tunnels might have frozen into place, leaving behind a network of higher dimensional highways embedded in spacetime like veins in marble. Detecting these relics wouldn't require telescopes but particle colliders. If extra-dimensional wormholes exist, they might betray themselves through subtle anomalies, particles disappearing and reappearing with slightly altered energies, as if they'd taken a detour through unseen dimensions. Some physicists argue that certain puzzling results at the Large Hadron Collider, like unexpected energy losses in particle collisions, could hint at this very phenomenon. Future experiments searching for gravitons hypothetical particles that carry gravity through higher dimensions might stumble upon wormhole signatures instead, catching whispers of the universe's original shortcuts written in the language of vibrating strings. This theory doesn't just offer a new way to imagine wormholes, it reshapes our place in the cosmos. If extra dimensions thread reality with hidden passageways, then mastering interstellar travel might mean learning to navigate spaces we can't even see, following trails blazed by the universe's first and most fundamental travelers long before stars began to shine. Imagine the universe as a frozen lake on the verge of thawing, seemingly solid and stable, but secretly harboring pockets of instability that could reshape everything in an instant. This is the essence of the false vacuum theory, a spine-tingling notion that our cosmos might not be in its most stable state, but rather perched precariously in a false equilibrium. And if that's true, the bubbles of true vacuum that could one day shatter reality might also forge something astonishing: wormholes erupting like cosmic escape hatches during the universe's most violent transformations. At the heart of this idea lies quantum field theory, which describes the vacuum of space not as empty nothingness, but as a seething quantum field humming with potential energy. Our universe could be trapped in a local energy minimum, a false vacuum like a ball resting in a shallow valley, unaware of a deeper valley just beyond the ridge. If a quantum fluctuation nudges the field over that ridge somewhere in space, a bubble of true vacuum would form, expanding at nearly light speed as it rewrites the very laws of physics in its wake. But here's the twist: the unfathomable energies released during this phase transition wouldn't just annihilate everything in their path. They might twist spacetime itself into tunnels, offering fleeting pathways out of the collapsing false vacuum. Picture a pot of water on the verge of boiling. As heat builds, vapor bubbles form not just on the surface, but within the liquid itself. Similarly, in the chaotic throes of a vacuum decay event, the boundary between false and true vacuum could become so warped that spacetime fractures into wormholes at the edges of expanding bubbles. These wouldn't be the carefully crafted tunnels of sci-fi, they'd be violent, unstable structures, forged in the cosmic forge of a universe rewriting its own rules. Some models suggest that the extreme pressure differentials between the decaying false vacuum and the newborn true vacuum could pinch spacetime into temporary bridges, like cosmic lifelines thrown across a collapsing landscape. The most startling implication: if such wormholes formed during past vacuum decay events, perhaps in the universe's earliest moments, they might still linger today as relics of these apocalyptic transitions. Certain anomalies in the cosmic microwave background, like unexplained circular temperature variations, could be the scars of ancient vacuum bubbles whose wormhole edges left permanent imprints on spacetime. Even more provocative is the idea that advanced civilizations facing imminent vacuum decay might deliberately trigger controlled phase transitions, creating emergency wormholes to flee the rewriting of reality, a last-ditch cosmic evacuation plan. This theory blurs the line between destruction and salvation. What seems like the universe's ultimate catastrophe could also be its most creative act, spawning shortcuts through the chaos like seeds scattered in a wildfire. If false vacuum decay can birth wormholes, then the universe's most dangerous instability might also be its greatest gift, a hidden network of tunnels woven into the fabric of reality, waiting to be found before or after everything changes. Quantum physics has long hinted at a strange truth: that the act of observation doesn't just measure reality, but might shape it. Now imagine taking that idea to its most extreme conclusion. What if consciousness itself, at sufficient levels of complexity and focus, could bend spacetime into wormholes? This isn't just wild speculation. Some interpretations of quantum mechanics suggest that observation collapses probability waves into concrete reality. Extend that principle far enough, and you arrive at a breathtaking possibility. that the universe's first stable wormholes weren't forged by natural processes or technological marvels, but by minds so advanced they could sculpt spacetime with thought alone. Picture an ancient civilization, not one that builds starships, but one that has transcended physical tools entirely. Through millennia of meditation, technological augmentation, or evolutionary leaps, they achieve a state where collective consciousness becomes a tangible force. When such minds concentrate on a single point in spacetime, their focused observation might resolve quantum uncertainties in ways that fuse distant locations together, threading reality with tunnels as effortlessly as we thread needles. The math behind this is as elusive as it is tantalizing. Certain models in quantum gravity propose that conscious observation could lower the energy barrier needed to stabilize a wormhole's throat, effectively turning intention into a cosmic glue that holds spacetime seams together. History offers eerie parallels. Double-slit experiments show particles behaving differently when observed, as if aware of being watched. Scale that effect up to a civilization harnessing unified consciousness, and the implications stagger. Wormholes might emerge not from equations scribbled on blackboards, but from harmonies of thought, their structures reflecting the mental patterns that birthed them. Some meta-studies of near-death experiences even report tunnels of light. Could these be subjective glimpses of consciousness briefly brushing against spacetime's malleable fabric? The most provocative evidence might lie in the universe itself. If consciousness can shape wormholes, then the distribution of galaxies or dark matter could reveal traces of ancient acts of mental engineering. Regions where cosmic structures align too perfectly or where gravity behaves unexpectedly might mark places where intelligence once reached into spacetime's foundations. Even the mysterious synchrony of quasars across billions of light-years long dismissed as coincidence could hint at a network of tunnels forged by minds we can scarcely imagine. This idea blurs the line between physics and metaphysics. If the first wormholes were products of consciousness, then the universe's oldest roads weren't built, they were dreamed. And if that's true, mastering interstellar travel might not mean constructing engines, but awakening to latent capacities within ourselves, rediscovering a truth written into reality at its birth. That mind and cosmos are far more deeply entwined than we ever dared believe. Plasma, that seething fourth state of matter, might seem too chaotic to build anything permanent, let alone something as finely structured as a wormhole. But in the extreme conditions following the Big Bang, plasma didn't just churn randomly. It could have self-organized into vast crystalline architectures, electromagnetic scaffolds precise enough to twist spacetime itself into tunnels. Picture the early universe not as a formless fireball, but as an intricate lattice of charged particles, their positions and movements governed by forces powerful enough to carve geometry into the fabric of reality. The key lies in plasma's hidden capacity for order. Under normal conditions, plasma, like that in lightning or stars, behaves like a turbulent gas. But when subjected to intense electromagnetic fields or extreme pressures, its charged particles can arrange into remarkably stable patterns known as plasma crystals. These aren't crystals in the traditional sense with rigid atomic bonds, but dynamic structures where particles align at precise intervals, held in place by electromagnetic repulsion and attraction. In labs today, we've created microscopic versions of these formations using radio waves and lasers, scale that up to the cosmic proportions of the early universe where plasma filled every corner of existence, and you have the ingredients for something extraordinary, crystalline frameworks large enough to warp spacetime on a galactic scale. Here's where the magic happens. As these plasma crystals formed and evolved, their electromagnetic fields wouldn't just arrange particles. They could twist the surrounding spacetime like a wire bending around a spool. General relativity tells us that energy and mass curve spacetime identically, meaning a dense enough concentration of electromagnetic energy, like that in a plasma crystal's lattice, could mimic the gravitational effects of a massive object. Now imagine two such crystalline regions aligning perfectly across vast distances, their electromagnetic fields resonating in harmony. The space-time between them might buckle under the strain, forming a tunnel where the fields overlap. Unlike wormholes held open by exotic matter, these structures would derive stability from the plasma crystal's inherent symmetry, its repeating patterns counteracting the tunnel's tendency to collapse. Evidence for this audacious idea might be hiding in plain sight. The cosmic microwave background, that ancient afterglow of the Big Bang, shows faint but puzzling irregularities, patterns of temperature variation that resemble the interference signatures of overlapping waves. Some theorists suggest these could be echoes of primordial plasma crystals, their electromagnetic footprints frozen into the sky as the universe cooled. Even more compelling are certain galaxy clusters that exhibit bizarrely synchronized orientations, as if their formations were guided by invisible scaffolds. If massive plasma crystals once permeated the cosmos, their remnants might still influence the universe's large-scale structure, like ghostly blueprints etched into space itself. The most tantalizing implication: nature might have provided a ready-made construction manual for wormholes. Advanced civilizations wouldn't need to invent stabilization techniques from scratch. They could study plasma crystals, reverse engineering the universe's own spacetime rending technology. Experiments in fusion reactors or quasars might already be creating microscopic versions of these structures without realizing it, their fleeting spacetime distortions dismissed as experimental noise. But if we learn to recognize and amplify these effects, humanity could unlock a paradigm where wormholes aren't cosmic rarities, but the inevitable consequence of matter and energy dancing to the universe's deepest rhythms, patterns older than time itself. What if the universe isn't the vast, organic reality we assume it to be, but an impossibly complex simulation, running on hardware built by minds we can't fathom? And if that's true, then wormholes might not be natural phenomena at all, but something far stranger: intentional glitches in the cosmic code, backdoors left open for traversal by the simulation's creators. This isn't just sci-fi speculation. Some physicists and philosophers take the simulated universe hypothesis seriously, and if they're right, then the shortcuts threading spacetime could be the equivalent of debug portals, hidden in plain sight by the architects of our reality. The logic here is as elegant as it is unsettling. Every simulation has limits: processing power, memory constraints, rendering distances. Even the most advanced system would need optimizations to handle something as vast as a universe. Wormholes could be one such optimization, shortcuts programmed to bypass the need to simulate every inch of spacetime between 2 points. Think of it like a video game loading screen. Instead of rendering every step of a journey, the system simply teleports the player to the next location. Wormholes might function the same way, stitching together distant coordinates without computing the space in between. But why would the creators leave these backdoors accessible? One chilling possibility is that they're not for us at all. They could be maintenance tunnels used by the simulators to observe or adjust the system from the inside. Alternatively, they might be relics of an older version of the simulation, bugs that were never patched out. Some theorists even speculate that these wormholes could be intentional Easter eggs, left behind as tests or challenges for civilizations advanced enough to discover them. Imagine uncovering a cosmic cheat code hidden in the fabric of reality, like a message in a bottle, except the bottle is spacetime itself, and the message reads, "You're not supposed to be here." Evidence for this idea could lurk in the very laws of physics. Wormholes violate no known physical principles, yet they require conditions so precise they seem almost designed. Their stability depends on exotic matter with negative energy, a substance that shouldn't exist under normal circumstances, yet fits neatly into the equations. It's as if the universe's rulebook includes a footnote: wormholes possible, but only if you know the override command. Even more telling are the mathematical coincidences that make wormholes theoretically possible. Constants and ratios so finely tuned they resemble the deliberate parameters of a programmed system. The most provocative clue might be the universe's apparent pixelation. At the Planck scale, spacetime itself seems to become granular, like a digital image zoomed in too far. Quantum mechanics, with its discrete energy levels and probabilistic outcomes, behaves less like a continuous reality and more like a simulation approximating one. If wormholes are glitches, their signatures could be hiding in the quantum foam, anomalies where the simulation's resolution dips, exposing the underlying code. Experiments measuring spacetime's fundamental granularity or quantum entanglement's limits might one day stumble upon these seams, revealing not just how wormholes work, but that they were never meant to be found at all. This theory doesn't just redefine wormholes, it redefines existence. If they're simulation artifacts, then traversing one wouldn't just be a technological achievement. It would be hacking the cosmos, slipping through the cracks of a reality we're only beginning to realize might not be ours to begin with. The first travelers through these tunnels wouldn't be explorers, but intruders, pioneers stepping into the debug mode of the universe itself. From the quantum whispers of vacuum fluctuations to the cosmic scaffolding of dark matter, the theories surrounding the universe's first wormhole travelers span an astonishing spectrum. We've journeyed through 30 wildly different possibilities, each one a doorway into the unknown. Maybe wormholes were forged in the violent aftermath of colliding neutron stars, their extreme physics twisting spacetime into fleeting tunnels. Or perhaps they emerged naturally from the chaos of the Big Bang, threaded through the cosmos like cosmic umbilical cords. Some theories suggest advanced civilizations cultivated microscopic quantum wormholes into interstellar highways, while others propose these shortcuts were accidental byproducts of higher dimensional physics or even glitches in a simulated universe. What's breathtaking isn't just the diversity of ideas, it's how each theory reshapes our understanding of reality. If wormholes can be spun from plasma crystals or stabilized by magnetic monopoles, the universe might be hiding infrastructure we've barely begun to imagine. The notion that consciousness itself could bend spacetime into tunnels turns physics into something almost mystical, and the chilling possibility that ancient time travelers left behind wormholes as relics of their meddling. That's not just science fiction, it's a challenge to rethink everything we assume about cause and effect. The beauty of these theories lies in their unanswered questions. Are wormholes nature's gift, woven into the fabric of spacetime from the beginning? Or are they the engineering marvels of civilizations so advanced they've mastered reality itself? The truth might be stranger than any single idea we've explored. That's the thrill of cosmic mysteries. They don't just demand answers, they rewrite the questions as we go. So now it's your turn. Which of these 30 theories resonated most? Do you think primordial black holes still hide wormholes in their hearts? Or are you convinced the quantum foam is bubbling with undiscovered shortcuts? Drop your favorite idea in the comments. We're all detectives in this grand cosmic mystery. And if you're hungry for more deep dives into the universe's wildest enigmas, don't forget to subscribe. The cosmos has endless secrets left to uncover, and we're just getting started. Who knows, the next theory might be the one that changes everything.